In this video, I want to walk you through two methods for finding unusual observations. It's a little bit different from looking at a single variable like we did in the prior video. Because conceptually this is going to be challenging if it's new for you, I'm going to prepare the data, make it really easy and ready to go, and then just focus on the new material. So in practice, you would have other things that you need to do to get the data ready, but I've done that for you. So we have two new packages, so this isotree and fnn, so that allows us to do the two other methods that we're going to introduce today. And we have a new data set. And I'm going to open the data set so you can look at it. Some of these things are going to be familiar here. So you've seen GV key as the company identifier before. The fiscal year end date, AT is total assets, and our Rev T you've already seen is total revenue. Then I have all of these other columns, and there are 42 or 40 something of those columns all the way up to here. So you have all of these things. And these are variables that are based on the income statement or the balance sheet and used to measure things about the company. And we won't spend too much time, worrying too much about what those things are. You just need to be aware that these are, for example, let me just show one of these. So for example, this one is asset growth. So the percent growth in assets. This one is cash and cash equivalents as a percent of assets. So these sorts of things. There are a lot of them here. But there are things about the company that happened in that year or related that could be measured in that year. So this would be 1995, the fiscal year 1995 for this company. And these are all measures from their financial statements. Okay, so it's all prepared. I've taken care of outliers. I've made it look sort of nice so the data is well behaved. Now once we have that and the data is nicely prepared, we want to say, can we measure how unusual particular observations are? And the columns that we're going to use to measure those unusual, like how unusual the observation is, are these columns. So these are all the ones that I created. There are some other columns in there, and we don't want to include them in the calculation. So this is where I'm going to use the select function. So select says keep these columns. So I'm going to keep only these columns here. You'll notice when you, sometimes the data could be grouped, and if it is grouped, it'll tell you that it's added another column. So here I'm ungrouping to make sure it's not grouped ahead of time, and I'm reading in from this CSV file. And then if there are multiple functions from different packages, so let's say I have select here and maybe there's a different package that uses select, I can tell it which select function to use from which package. So here I'm telling it look in the dplyr, the dplyr package. So you do the function, the package, 2 colons, and then the function. So this tells it use the select function from the dplyr package. That's only necessary when there are conflicts, so I'm just showing it to you so that if you run into a conflict, then you can know how to tell it where to find the function. Otherwise, you could just put select here and it'll work just fine. Okay, so we run this, we get this data. The big difference here is, notice I got rid of all of the other columns. This is only the columns that I'm going to use to try and measure if one observation is different from another observation. And by observations, I mean rows. So how much is row 1 different from row 2 or row 3 or any other row of these 58,000 rows? And there are a couple of ways we're going to do it. This will take a little bit of work in class, and then also you could go read about some of this. So the first one we're going to use is a distance measure. So it measures how similar one observation is from another, so it's going to say compare revenue growth for row 1 to revenue growth from row 2, and it's going to create a distance measure, meaning how different are those, and it's going to combine them for all of these columns. So how different is column 2 for row 1 versus row 2, and similarly through all of these, and it summarizes them in a distance function. And so we'll go over that in class, or you can look here at this website. It talks a little bit about these distance functions, and there are other ones you can learn about also. You can just search up KNN, or K nearest neighbors is what KNN stands for, or distance measures, and you'll find out information about that. So I'm going to use the function from this FNN package here. It says get the K nearest neighbors, so this is going to measure, going through every row of the data, how is row 1 compared to row 2, and then how is row 1 compared to row 3, and then I'll go all the way through that data. Then it'll start with row 2, and then look from how different is row 2 from row 1, and then how different is row 2 from row 3. And so the problem with this sort of approach, it's very conceptual and works great. The problem is that it can run for a long time, because for 58,000 observations, it has to go through every row, 417,000 times. So 58,418 times 58,418, it's a lot of times that it goes through the data. And K here, so this is the data we're using. K tells it how many nearest neighbors to keep, so it goes through every one and then keeps the N nearest neighbor, or the K nearest neighbors. So in this case, I'm telling it to use the 50 most similar observations. So for row 1, it's going to look at the 50 closest rows in the rest of the data. And then what comes out of this is an object that is from this. So we have this index, it's a big matrix, and then this distance measure. So notice it goes every row, so that means for row 1, and then it's going columns 1 to 50 columns. A big matrix. It has 50 columns because I told it to keep the 50 nearest neighbors. You could do the whole data set, but that would be a lot of memory and then take a lot of time. Okay, so for every row, what are the 50 nearest neighbors? And we can look at, we've got 2 columns or objects in this NN object. So it's a list, and we've got a list of a list. So here this NN.dist is what we're looking for. This is how different, what is the distance between row 1 and column 1. So it's going to go through each of these, or sorry, row 1 in the data versus row 2 in the data, for example. So we can go ahead and look at this. I'm going to look at this distance part of the list, or this matrix. So I'm going to look at rows 1 to 5 and columns 1 to 5. So these square brackets are telling it which cells to look at, and then 1:5 says go 1 to 5. So this is what this NN.dist matrix looks like. So for row 1, it gets the nearest neighbors, the 50 nearest neighbors in all of the other rows. So here it's just showing the first 5, but this first row, the distance between the first row and then whatever this nearest neighbor is 0.1. The next one 0.15. So notice it goes up. So the one that is closest to this row 1 is whatever one it found here. The smallest distance measure is this 0.1, and then it gets larger as you go out to 50. So each of these rows is going to be different. Some rows are really similar to other rows are very different, and we're going to try and calculate sort of these 50, on average, sort of how close is row 1 to other rows, and we're going to use those 50 closest rows. And how we're going to do that is this row means. So row means, so it takes the means of the rows. That's what it does. So it's going to take the average across all of these 50 here. So the average of, this, 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 all the way out to the 50 columns we have. And we're going to put that in the original data set, and we're going to call it unusual underscore KNN. So K nearest neighbors distance function is what we're looking for. Once we run that, we can look and see in the original data set, I've got a column towards the end here that is unusual underscore KNN. So on average, row 1 has a distance from other rows of 0.14. This one is a little more, has a larger distance on average from its nearest neighbors than row 2. So row 1 is a little more unusual than row 1, and row 3 is more unusual than row 1 or row 2. So these sort of give us an idea of how unusual something is, going from whatever low to whatever high value. And we can even sort by this and look and see. So on the low end, 0.09. On the high end, 8, 4, 3. So these are the ones that are the most unusual in the data set, meaning it can't find observations that are really close to that row given this distance metric. Okay, so that's one approach. The disadvantage of this is it could run for a long time. So I made a note here. It can run anywhere from 5 to 20 minutes. Just takes a while. So you may want to try this and then walk away and come back later to see if it finished. Then the other one we're going to use is called an isolation forest or isolation tree, and this is based on a tree-based method. So it's a machine learning approach that splits rows into groups, and we'll go over this more when we go on to tree-based methods. But it's splitting it up to say, can we find similar groups for all of the rows? And it's doing it by guessing cuts in the data and how to make things similar or not similar. So that's about as much as I'll get into that. Here is a site that you can go look and read a little bit more about that. But it's the same concept, finding unusual observations. The advantage of this approach is it's much faster because it doesn't have to go through every single row, and the scale of the variable, if your data is really clean or different size scales of the columns, it won't matter as much as in these distance-based measures. All right, so we run this. The function is isolation.forest, same input data. It's going to output a bunch of stuff here, and it's called a model, so I called it ISO model. And then there's a lot of stuff in this ISO model object that tells us about how it estimated it and things like that. Not incredibly easy to understand, but what we're going to do is from that model predict. So predict is a function that we use a model, then predict what the outcome of that model would be. So for each row in using this ISO model, for each row in the temp data, which is our original data, we are going to predict how unusual that observation is. And we're going to put that into the same original data set. I'm going to call it unusual underscore ISO. So we go ahead, open that data again, and look at the last column, and it's the same sort of thing. So this tells us how unusual the observation is based on this model, and we can sort it and see, 0.3 is sort of the low, 0.69 is the high, so we sort of have a range between 0.3 and 0.7. So then what can we do with these, right? We want to know, like, what is it about those observations that are unusual? In practice, we might, we could use it in an auditing task, or we could use it in other things where we're trying to come up with red flags. But the idea is to say, once we see that it's unusual, then we go look and understand it more. So to get an idea of this, I'm just going to do some correlations here. So the core function, and I'm going to correlate the unusual measure, so KNN and ISO, see how correlated it is with the log of revenue. So remember, revenue can have some extreme positive values, so by taking the natural log, that helps it be a little more like a normal distribution. So I'm going to do each of these, so let's go with these first. So the correlation with revenue. So notice higher revenue is a lower unusual measure, so larger revenues seem to be associated with being less unusual. So if we reverse that, small revenue amounts are associated with being an unusual observation. So we have data that is that the smaller companies are more unusual because they don't match along all of these other dimensions. So small companies are harder to understand, basically, based on the data we have. We'll do the same thing with assets, and you'll see the correlation is pretty similar. So larger companies based on assets are less unusual in the data. So if we wanted to throw up some red flags, then we would say in the very small companies is where we are going to find potential problems. So this is the type of thing that like the SEC would do, trying to look at the companies that are the highest risk because they have unusual outcomes. Same thing we can do here. And it doesn't have to be companies, right? It can be transactions, it can be whatever sort of data you have to try and figure out which ones are unusual, as long as you have a fairly good number of columns that you create about those observations. So I already showed you this. We could sort and look and see what are the really unusual ones. So let's look back here. So the really unusual based on the KNN measure, notice the second most unusual is very small, so it has less than $1 million in assets, less than $1 million in revenue. The top one, less than $1 million in revenue, but more in assets. But it's not only the small ones, so notice we have some very large values that also make the observation unusual. So even though the correlation says that in general smaller companies are more unusual, we still have some large ones that are also unusual here. So let's say these were companies that you were worried or have some accounting issues going on because you're with the SEC, then you might sort of take the most unusual ones here and go investigate more closely. What are these ones? Why are they so unusual? What's happening to them? Then we're going to turn to KNIME and do the same sort of thing. So have fun with this. We're going to mess around with it a little bit and try different things. In terms of the amount of code, it's not too difficult, but I think conceptually getting this under your fingers may take a little bit.